In this video, we're going to take a look at what happens if we want to evaluate a definite integral that requires integration by substitution to find its antiderivative. If you're following along, I did kind of jump ahead here to the not the next page, but the one after that, and we're going to come back and look at those other integrals in just a moment. So here I have the definite integral from 2 to 5. I have square root 6 minus t dt here. So I start this off, I say, okay, maybe we want to rewrite that radical. This is really the definite integral from 2 to 5. This is 6 minus t to the 1/2 power dt. We say, okay. I look at this, I think we pretty much have to use substitution here. If I look at what's inside of that power, it's 6 minus t. As long as you have anything more complicated than just t, we're going to have to use substitution. So no matter what, now I want to show you two different ways to use substitution within definite integrals. Your substitution is going to start the same no matter what. So I'm going to pick u equal to 6 minus t. du is equal to, let's see, derivative of 6 minus t. That would be -1 times dt. So I look at this, I say, okay, here is u, that's 6 minus t. I don't have a -1 to deal with here. I really only have the dt. So let's multiply both sides by -1 just to get rid of that. So -1 times du is equal to dt. So when I make my substitution, this is -1 times dt. This right here, this is u. So when I perform my substitution, it's going to act very similarly. Here I see that -1. Let's go ahead and factor that out right away. -1 times the integral, I'll have u to the 1/2 power du. Oops, I realized I made a mistake. I said -1 dt. This should have been -1 du. I apologize. Here's where our two methods of evaluating these definite integrals with substitutions is going to start to change. The way I prefer to do them is I'm going to look at my lower limit of integration and my upper limit of integration. Because right now, these are actually in terms of t. This is t equals 2 and t equals 5. I'm going to take those, I'm going to rewrite them so that they're in terms of u. So let's do that down here. Let me do that in a different color. So when t equals 5, u equals 6 minus 5, that's equal to 1. So look at where 5 was. 5 was my upper limit of integration, which means that 1 is my new upper limit of integration in terms of u. This is really u equals 1. Which you don't need to write u equals 1, but I really want you to understand that now I've translated that upper limit of integration to be in terms of u. And I'm just taking that number and plugging that in right here. So when t equals 2, u is equal to 6 minus 2. This gives me 4. So my lower limit of integration now is 4. So this is the new definite integral that I'd like to evaluate. And if I'm using this method of integration by substitution, I basically forget that there was ever, a 6 minus t or anything like that. I basically pretend that this is my new problem. This is what I'd like to evaluate. One thing I'd like to mention before I continue, notice here that the upper and lower limits of integration, up until this point, the upper limit of integration has always been bigger than the lower limit of integration. This does not have to be the case. If we're talking about area under a curve, yes, that's what we want. But especially if we're doing substitution and we translate these limits of integration, don't overthink them. 5 was our upper limit of integration, and we found 1 by taking 5 and plugging it in for t. So that means 1 is our new upper limit of integration. So I'm going to continue on with this problem. So the -1, we're not going to worry about that till the end of the problem here. Let's see, I'm going to add 1 to the power, so this will be u to the 3/2 power times 2/3 times the reciprocal. And I'd like to evaluate that at 1 and 4. So this is really -1 times 2/3. Let's just say -2/3. Notice I'm not going to take my 6 minus t and plug this back in for u. Since my upper and lower limit of integrations are in terms of u already, I don't need to take 6 minus t and plug that back in. So -2/3, my upper limit of integration is 1 to the 3/2 power minus -2/3 times 4 to the 3/2 power. So let's see, -2/3, 1 to any finite power is 1. Let's go ahead and say that this is plus a positive. Let's see, 4 to the 3/2. Square root of 4 would be 2 times 3 would be to the third power would be 8. So this is 2/3 times 8. So I have -2/3 plus over here I'll have 16 over 3 gives me 14 over 3. So this is the first method that you can use. This is my preferred method to evaluate definite integrals using substitution. It's more consistent. And I'm doing air quotes here, the right way, and I'm also kind of rolling my eyes a little bit too. Because we translate these limits of integration to be in terms of u. Now let's say you just didn't prefer that method and you really wanted to see a different way. We can absolutely do that. So we said, okay, we were integrating 6 minus t to the 1/2 dt from, I already forget, 6 minus t from 2 to 5. The beginning part of this problem is going to be almost identical. So you're still going to pick u equals to 6 minus t. You're still going to say du is equal to -dt. And we say, okay, we got to get rid of that -1, so we'll multiply both sides by that. Negative du is equal to positive dt. So then we say, okay, this piece right here, that's my u, and then this piece right here, that's negative du. All of that is exactly what we did in the first part. So when we make our substitution, it's going to look mostly the same. The -1 still on the outside. I have u to the 1/2 power du. But I'm going to leave these as they are. I'm going to leave those as 2 and 5. And this is one of those things that, as a math teacher, just makes me kind of cringe and makes me go, I don't like it. And the problem is that these limits of integration are in terms of t, and your integral is in terms of u. This is technically wrong to write it this way. Now I say technically wrong, but we can kind of account for it later on in the problem. The way we'll do that is we'll actually perform the second substitution that we didn't do in the last example. So we're going to leave our lower and upper limits of integration. Just make sure you're careful with this one. So we'll I don't know what happened there. Perform our integration. So this will be u to the 3/2 power times 2/3, evaluated at 5 and at 2. But remember that these are in terms of t. So what we need to do is take that 6 minus t and plug that back in now. So this is -2/3 times 6 minus t to the 3/2 power, evaluated at 5 and 2. Now when we write it like this, everything is in terms of t again. Everything's going to be okay from here on out. So this would be -2/3 times 6 minus 5 to the 3/2 power minus -2/3 times 6 minus 2 to the 3/2 power. Let's see, this will be -2/3 times 6 minus 5. That's going to be 1 to the 3/2 is 1. Plus 2/3. This is going to be 4 to the 3/2, which is 2/8. That's exactly the same thing we had in the last one, so we get 14 over 3, which is exactly the same solution. So it doesn't matter which method you use. Like I said, I prefer this first one. This is how I'm going to be doing my problems and examples going forward. But if that just isn't working for you for whatever reason, you can use this second method and it's perfectly fine. You'll get all of the same answers. It's the same amount of work. It's just kind of how do you want to split that work up. Here we kind of split that work up a little bit more evenly, do some of it at the beginning, some of it at the end. I always felt like when we look at here, this end part right here, when we're evaluating this piece, you're kind of doing a lot at once, which is another reason why I just don't think I really like it. So let's look at a couple more examples using substitution. Do a couple more here. So here I have the definite integral from 0 to 1 of 1 over 2x plus 4 dx. So let's see, I'm going to pick u equal to 2x plus 4. And I'm going to pick du then, du derivative of 2x plus 4, that'll be 2 dx. So right here's u. This piece right here then, oh, I only have the dx, I don't have the 2 right here, so I need to get rid of that. We'll multiply both sides by 1/2. So 1/2 du equals dx. The 2's will cancel over here. So I'm going to take this piece out, replace it with 1/2 du. So let's see, I'll factor the 1/2 out first. This is the integral, let's see, of 1 over u du. I'm going to take these limits of integration and rewrite them here. So let me change my color to do that. So I'm going to be using this expression. So let's start with our upper limit of integration. When x is equal to 1, u is equal to 2 times 1 plus 4. This is 2 plus 4. U is equal to 6. So since 1 was my upper limit of integration originally, that means that u equals 6 will be my new upper limit of integration. Next, I'll take my lower limit of integration, 0. X equals 0. U is equal to 2 times 0 plus 4. This is really u equals 0 plus 4, which gives me 4. So since 0 was my lower limit of integration, that means that 4 is my new lower limit of integration. And what this means now is that I'm just essentially almost starting this problem over. I'm saying, hey, I'd really like to evaluate this definite integral. So let's see. When we do that, we'll have 1/2. This is natural log absolute value of u, evaluated at 6 and 4. And remember, because these are in terms of u already, I do not need to take that 2x plus 4 and plug that back in. We can just go ahead and say this is 1/2 natural log absolute value of 6 minus 1/2 natural log absolute value of 4. Maybe we'll just get, I'm going to get rid of the absolute values here since 6 and 4 are already positive numbers. There's no reason that we need them. I'd probably leave my answer like this. But of course, you could get a decimal approximation. Just type that into your graphing calculator. Let's look at one more example before we wrap this video up. Here I have the definite integral from -10 to 25. I have e to the negative 0.01x dx. So again, I need a u. So let's see, u. Hopefully we see this exponential. We say, oh, that's got to be the power. U is equal to negative 0.01x. So du, the derivative, is negative 0.01 dx. So I say, okay, this power right here, that's my u. So this piece right here, I'll underline it. This is my u. All I have is this dx left. So that means all I want in this expression is dx. I'd really like to get rid of that negative 0.01. So you could divide by negative 0.01 if you'd like. Probably the easier way to write that, if you take 1 divided by negative 0.01, you actually end up with negative 100. So I'm just going to multiply both sides by negative 100. It'll just look a little bit nicer. So I end up with negative 100 du equals, over here these two are going to cancel, just dx. So this piece right here, this is negative 100 du. So let's perform our substitution. The negative 100 is a constant multiple, so we can bring that out front right away. Times the integral, I should have e to the u du. So I performed my substitution. I now need to rewrite my limits of integration. So we'll take those off to the side over here. So these are x values. Let's start with our upper limit of integration, 25. When x equals 25, u is equal to, and again I'm looking at this equation right here, u equals negative 0.01 times x. So negative 0.01 times 25. I should end up with negative 0.25. So negative 0.25, that is my upper limit of integration. When x equals negative 10, u is equal to negative 0.01 times negative 10. Here I should end up with a positive 0.1. So that means my lower limit of integration was 0.1. So this is my new definite integral that I'm trying to evaluate here. So okay, negative 100 is a constant multiple. We're not going to worry about it. The antiderivative of e to the u du, that's just e to the u evaluated at negative 0.25 and positive 0.1. Notice here again that the upper and lower limit of integration don't necessarily follow that pattern of the upper limit of integration being greater than the lower limit of integration. Don't try and fix it. Don't overthink it. Just leave it as it is. And then I need to just plug these values in. So I should have negative 100 e to the negative 0.25 minus negative 100 e to the 0.1 power. Minus negative, of course, plus a positive, and then you could go and get a decimal approximation there if you'd like, but that is our solution. So be careful when you're working with integration by substitution and definite integrals. Make sure that you're changing the limits of integration if that's the method that you choose to use, or that you take, in this case we would be taking negative 0.01x and plugging that back in after we found our antiderivative. You're doing one or the other of those two. You are not doing both.